Technology is conspiring against me. Oh boy. Matt, are we coming through okay? All right. Well, y'all get to see the back of my head today. I can't get the electrons to turn around the right way. Okay, we're going to take a look at some, I've introduced the idea of the root locus last time we met. And so today I want to do some examples. And with each example, what we want to do is try to come to some general conclusion about what the root locus diagram ought to look like. So basically what we want to do is walk out of here at the end of the week with a rough idea of what are the general rules for sketching them. It turns out that when you draw a root locus diagram, there's not a particular procedure where you got to do step 1, step 2, step 3. You just got a bunch of characteristics that need to be all satisfied. But the particular order that you do them doesn't really matter. Now, some of the characteristics are easy to do, so you might naturally want to do them first. But that doesn't mean that you have to do them first. It's just that the characteristics all need to be satisfied. And we're not here trying to draw a really accurate diagram by hand. Maybe next time we meet, I'll show you how we used to do it accurately by hand. There's actually a special tool for drawing things by hand. We don't use that anymore because we now use electrons when they want to help us. Okay, so we're going to take a look at some characteristics. And what we're going to do is we're going to use a command in MATLAB called rlocus, R-L-O-C-U-S. And the transfer function is going to be G. That's the command in MATLAB, all right? So I've got on tap this morning maybe 6 or 7 examples, and we're going to take a look at each of the different examples. And I'll talk through each picture, and then we will kind of summarize things. All right, so the first example. Well, let's construct that function, that model, that process in MATLAB. Okay, remember the root locus problem looks like this. Let me back up, go back to the control system. We're analyzing this control system. K is a parameter that varies from 0 to infinity. We're dealing with positive root locus. There are rules for negative root locus. The computer can calculate it instantly, almost instantly, if you want to do it. But when you execute the plain old root locus command, it's going to assume you want the positive root locus because that's the most common problem that we deal with. And then we're given the process model. So we'll always use the process model. And what we're trying to do is predict behavior of this closed loop system. So again, use open loop information to predict closed loop behavior. So the first model is S plus 2 over S. You might do it like this. Let's call it G1. G1 is a transfer function. The numerator is S plus 2. And the denominator is just S with no constant term like that. Okay, and do rlocus, execute the rlocus command. And you should get a picture that looks like this. First of all, notice how the axes are labeled. These are plots of poles. Poles can be complex numbers, so this has to be the S-plane. And we start off with the open loop information. And the open loop information in this case are the poles and zeros of this system. And so we have this, and we have this. We denote the poles with X's and the zeros with O's. Okay? O's or zeros. And this is located at -2. So you should get a picture that looks like this, X and O, and then it's going to fill in right here. Okay, to draw a picture like that. I don't think MATLAB draws an arrow, but I'm going to draw an arrow like this. Does MATLAB draw an arrow? No, okay, it just gives you a line. So how do I know where the arrow goes? Well, let's make some generalizations. The loci, this is a locus, it's a set of points, It's the set of all possible closed loop poles. The open loop poles are x. There's only one. It's x. I mean, right here. It's at s equal to 0. But when I close the loop, the control system, which I drew up here, has different poles. It has a different model. It has different poles. And the poles lie somewhere in this segment between here and here. They will only lie between 0 and -2. There won't be any other values as I adjust k from 0 to infinity. So these are the poles as k goes from 0 to infinity. And one of the generalizations that we can make here is that the loci, let's make one generalization. They start at the open loop poles. See how this branch starts at the open loop poles? And they terminate on the open loop zeros. Okay. Or they'll terminate somewhere else, but this example doesn't show where they may terminate. Okay, so I'm going to leave you hanging here. We'll see that in the next example, all right? All right, the other thing, let's do another example. We'll call that one G2. So let's leave all these G's in your workspace, and let's do a second example, G2. So it's a little bit more complicated. This is a second order system, 2 poles in the bottom. It's also got 2 zeros in the numerator. And so you would describe it in MATLAB this way. The numerator has coefficients 1, 2, and 2, and the denominator has coefficients 1, 1, and 0. Do R locus. And let me sketch the picture again. Label things real and imaginary. This is the S-plane. Let's sketch in the process poles and zeros. So we have a pole here at the origin, a pole here at -1, and then we have a couple of zeros. These are complex. These are here. The zeros are at -1 plus J1 and -1 minus J1. I think you should get a picture that looks like this. All right? Now this picture will look something like this. There's color in between here, and then there will be a branch that looks like this and one that looks like this. Okay. So the previous conclusion still holds true. The loci start at the open loop poles and they end on the open loop zeros. They start right here, and they terminate here and here. So let's make some more generalizations, maybe. The number of loci, how many branches are there? And the number of branches, I call them branches because they look like branches on a tree, but the textbooks will call it loci. The number of loci is equal to the number of open loop poles. Okay. This previous example number 1, first order system, only one branch, one locus. This system has second order, so there are 2 loci in the root locus. The other thing that you notice is since we're dealing with complex numbers and we're dealing with physical systems, these coefficients up here in the model are all real numbers. Okay? Since these are all real numbers, the poles, any roots, they're always going to be complex conjugates. So you see the zeros were complex conjugate pair. If we had poles that were complex, they would be complex conjugate pairs. Everything always comes, if it's complex, it's going to come in a pair. So that means there's going to be symmetry. And so the second thing we should see is that the root locus is symmetrical. It's symmetrical with respect to the real axis. Okay, so if on an exam we were given this problem and we were to start it, we would label our axes. We'll put in our poles. We put in our zeros. And then we say, oh, the loci start at the x's and they end on the o's. So you might say, well, we'll draw a picture that looks like this. Okay, there's a problem here. This is not symmetrical with respect to the real axis. Okay, that would not be a valid root locus diagram. Okay. Now, you may start asking, well, is it exactly this? My shape, I'm not even sure my shape looks exactly like what you got on the screen. It's maybe roughly correct. And you may be asking, where exactly in the middle does it break? This is called a real axis break right here, where it turns from real and becomes complex. There are actually formulas that can be used to calculate those things. And when I was in school, we had to learn those things because we were doing everything by hand. We don't do that anymore. The book will give you the formula, but I'm not going to hold you accountable to it. What I would like for you to be able to do is at least get a rough sketch that looks something like this. Okay, take a look at your picture. All right, any questions about this second example? I think the takeaway so far is loci start at the x's, end on the o's, draw a picture that's symmetrical. Okay, they start on the x's, end on the o's, but like I said before, there's an or. I left you hanging, and I'm still leaving you hanging because there's nothing different here. But let's do a third example. A third example, G3. This was G2 earlier. Let's go with G3. G3 is a very simple model like this, 1 over S. It's an integrator. It's a pure integrator. It's a capacitor. It's the model of a capacitor because the capacitor voltage is 1 over C integral of I dt. Or it's an inductor. Okay. I is equal to 1 over L integral of V dt. So, oh no, did I say that right? Yeah, V equals L di dt. So G3 is a transfer function. The numerator is 1. And the denominator is S, like so. Sketch our axes, real and imaginary, and there's the model. Okay? Do root locus. The generalization, we saw it before, is, well, the loci should start at the x's and end on the o's. There are no o's. So that means, earlier, when we said O, or, when I said or, what is or? The or here is they go off the page. Now the textbook will use this term. Zeros at infinity. They're calling the edge of the paper 0. Okay, it's a 0 off the page at infinity. They call it zeros at infinity is another way of just saying it goes off the page. Okay, because the locus looks like this. Okay, as k increases, the closed loop pole gets more and more negative like this. It's just a line that goes off like this. Okay, let's review some of the generalizations. The loci start at the open loop poles, they end on the open loop zeros, or they go off the page. The number of loci is equal to the number of poles. There's only one pole, there's only one locus. The locus is symmetrical with respect to the real axis. Yeah, it's symmetrical with respect to the real axis. Okay? Now, you may ask, well, how do I get off the page? Why did you draw it this way? Turns out that there is a rule for graphing which direction it goes off, because I could draw a line that goes off in other directions. I won't go over the formula yet. Let's do a few more examples, and then we'll kind of summarize how these go off the page things work. All right? Let's do another example. Kind of slide this up here maybe. S plus 2 over S squared. 2 poles, 1, 0. This is G4, fourth example. It's a transfer function. The numerator is S plus 2. S plus 2 like this. And then the denominator is S squared. S squared is going to be 1S squared plus 0S plus 0 constant, like that. Do the root locus again. Label our axes real and imaginary. And let's put in the poles. There's 2 poles. The nice thing about doing it by hand is you can draw it like this and make it look like it's got 2 poles. The computer is going to draw it very accurately. And it's going to put 2 X marks on top of each other, and you're saying, why are there 2 lines emanating from one point? You know, let's see, there's a 0 out here at minus 2. Okay? And this picture is going to look like this. I can't draw a circle standing backwards, but this is supposed to be circular. Okay? All right, so let's review again some of the generalizations. Model number 1 told us the loci start at the open loop poles, the X marks, and they end on the O's. They start on the X marks and they end on the O's, or they go off the page. And here's an example where we have both cases. We have 2 poles. That's another one of the generalizations. It means we have 2 loci, 2 branches. In MATLAB, are you seeing 2 colors in your graph? What are they using? Blue and green? Blue and green. Okay. Is that really happening physically? Is there, no, these are just mathematical tools, okay? They're just mathematical tools. And as MATLAB is calculating them, remember how we did in class, we did a table manually, and we made a column and listed all our poles. Imagine MATLAB doing that also, and now it's just graphing one column, calling it blue, graphing the other column, calling it green. You said blue and green? Yeah, blue and green. All right. It's not sacred which way, you know, which one's blue and which one's green, but you see there's 2 X marks here. You won't see it on the computer screen. It'll look like 1 X mark, but you'll see 2 things coming out of it. And then they break back in here, and then as the gain K further increases, one of the closed loop poles will move this way toward this, and one will go this way. Okay? So we saw X's go to the O's, or they go off the page. Again, we have one of them going off the page. The number of branches or number of loci is equal to the number of poles. We see that the picture is symmetrical. I said there's a formula for calculating what this point is, but I'm not going to hold you to it. So it's not so terribly important because we have a computer to do it for you these days. You just want right now to get a rough idea of what's going on, so you have a sanity check in your head. Now, you may be asking, well, could I draw a picture that looks like this? Maybe I'll draw a picture that looks like this. Okay, these are to be symmetrical. How do I know it doesn't do that? You don't. Okay, you don't. Not easily, not without some more experience, and not without a little bit more confidence in your math. Simple functions don't behave in funny ways. And so if it behaves something like this, there must be something more complicated in the model. So that's one of the reasons. You don't get discontinuous behaviors out of plotting polynomials. Polynomials inherently are smooth. Okay, and so the other thing you may ask is, how do I know this thing doesn't, say, approach and break in kind of asymptotically like this? Okay, instead of coming in at kind of a 90-degree angle right here. Why is it 90 degrees right there? And why is this 90 degrees right here? And why is this 90 degrees right here? There are some formulas that can allow you to calculate at what angle you depart from the real axis. And at what angle do you approach the real axis if you're going to break in? There are formulas for that. But it turns out that, they're not going to approach like in this manner for this case. So some of it is going to just come by experience. All right? We'll do an example maybe later where the breaks are not 90 degrees like this. They can be other angles, but they won't be kind of some smooth asymptotic approach. They're going to just break in at an angle. Okay, that's problem number 4. Any questions about problem number 4? Any unusual characteristics you want to ask a question about? All right, let's do problem number 5. Okay, 1 over s squared plus 2s plus 1, a second order model. This might be the model of a RLC circuit. That's second order, or an LC circuit. No, not LC, because this one's got 2 real roots. It has to have R in it because it's critically damped. It's got 2 poles. An LC circuit would be a pure LC circuit would be an oscillator. It has no damping. It would have complex poles. This one has real poles, so it's an RLC circuit. The numerator is 1. The denominator is s squared plus 2s plus 1, like so. Let's do root locus. Label real and imaginary. Sketch in our open loop model. The open loop model's got 2 poles right here. Okay. There are 2 branches. They're going to start at the X marks, so I need to draw 2 branches that start at X marks and they go to the O's. There are no O's. There are no zeros. There are no open loop zeros. So that means everything goes off the page. That was another one of our generalizations. And it turns out that they're going to go off the page like this. Okay. In an earlier model, let's see, the model in G4, there was only 1 going off the page. And you see it went off in the minus 180 degree direction. It went off this way. Now with 2 going off the page, they kind of go off the page this way. So think about some generalizations. Right? Let's see. Loci start at the X marks and they go to the O's. There are no O's, so therefore they go off the page. The number of loci is equal to the number of branches. I mean, the number of branches is equal to the number of poles. This is a second order system, so there's 2 branches, 1 going up, 1 going down. Blue and green. I don't know which one is which. What else? Symmetrical. Notice that the picture is symmetrical with respect to the real axis. All right. Let's pretend now that we're going to say we're going to add a control. We're going to make our system a little bit more complicated. We're going to do this control system now. We still have 1 parameter that's adjusted, k. The root locus problem assumes that the parameter being adjusted is here, it's k. But we could have a more complicated system. Let's have a compensator right here. And then we have our plant, the model that we just put in, G5, like this. All right, that's the system we want to analyze now. So we already have this model. Let's put in a model for this. Let's do 2 models. Let's do let's do C1 of S is equal to S plus 3 over S plus 10. Okay. So you would say C1 is a transfer function. The numerator is S plus 3. The denominator is S plus 10. Now we've been studying lead and lag compensators. Is this a lead or is this a lag? I got 1 0 and we've got 1 pole. Remember, what's the difference between lead and lag? This is a lead. Why is it a lead? The poles that are higher frequency than the zero. Okay, so this is a lead. So let's see what happens if we use a lead compensator. All right. The other one, let's swap it. Let's call it S plus 10 over S plus 3. This is a lag. If you want, you can say C2 is equal to 1 over C1 in MATLAB, 1 divided by C1. Or you can enter in transfer function and type it all out. So now we've got these two compensators, and we're going to try to do a root locus. All right? Let's do both root locuses, but let's do it in 2-figure windows. And so let's do it like this. Let's plot in figure 1. Let's do the root locus. I want to do the root locus for this control system. So if I want to do the root locus for this control system, what is the model that needs to be entered in? Do I calculate the closed-loop transfer function? Raise your hand if you say, we've got to calculate the closed-loop transfer function. No, we don't, right? That's the whole point of using the root locus. We don't calculate the closed-loop transfer function. We need to calculate the open-loop model. So what's the open-loop model? K is being adjusted, so the only thing that's left is C and G. Okay, so we have to do root locus. We need to feed it C and G. We've got two C's we want to try out. Let's do this one. C1 times G5. The model was G5, okay? G5 was this model. So we're going to do that, and then we're going to continue on, but let's open up a second figure window. Let's call it figure 2. And let's compare it, and we're going to do C2 times G5. And let MATLAB grind away. You should see two windows pop open. In one window, let's plot the open loop poles and zeros. We've got, those are the plant poles, G5 poles. It has no zeros. But then we added a lead. And the lead we added was at -3. And way out here at -10. Okay. And this picture is going to look like, there's something here, and I got to figure out where it's going to go off the page. It's going to go off the page at, let's see, minus 10, -1 is -11. -11 plus 3 is 8. 8 divided by 2 is 4. Okay. Kind of draw a line vertical right here. I think this line goes through the point -4. And so the picture will look something like this. Okay. Is this vertical line kind of right around -4? Yeah. Is it -4? Yeah. Okay. So again, let's review the properties that the root locus diagram satisfies. It's in the S-plane. The loci start at the X marks, and they go to the O's, or they go off the page. Starting at the X marks, these two are going off the page. This one is going here. The number of branches, the number of loci is equal to the number of poles. I have 2 plant poles, 1 compensator pole, so the overall system is third order. And so I have three loci. One's going this way as k increases, goes from x to O. The other two go like this. And again, the arrows are drawn by my hand. They're not drawn by computer. Will this control system be stable as I increase the gain? How do we answer that? We have to answer that by looking at where the loci are. Do the loci ever go into the right half plane? They never do. So the answer is it stable for all k? The answer is yes. Now in the other figure window, we get a picture that looks like this. We've got the two x's for the minus 1. At minus 1, that's the plant poles. But then we have a pole at minus 3. And then way out here, we have a 0 at minus 10. I reversed the location of the 0 and the pole of the compensator. So this is the lead case, and this is the lag case. Real axis, imaginary axis. And so this is going to be, let's see, minus 4. Minus 4 plus 10 is, minus 4 plus 10 is 6. Divided by 2 is 3. So out here at around positive 3, you can draw a vertical line, and then the picture is going to look something like this. Okay, let's review the rules again. The number of, let's not do it in the order I've been talking. How many loci should there be? The order is 3, so there should be 3 branches. Is the picture symmetrical? Yes. What else is a characteristic? The loci start at the X marks and they go to the O's. Or they go off the page. Okay. In both of these cases here, number of poles is equal to 3. Number of zeros is equal to 1. The difference between them is a name that we call the relative degree. We did this in Bode plots. It's called the relative degrees. The difference in the degree between the denominator and the numerator. 3 minus 1 is equal to 2. So relative degree is 2. What else is 2 here? What else is 2 here? What do we see 2 of here? Two things going off the page. Okay? 2 things going off the page. 2 things going off the page. In the previous example with G4, number of poles is 2. Number of zeros is 1. Relative degree is 1. Only one of them going off the page. Okay, so the number of things that go off the page is equal to the number of, is the relative degree. Okay, so maybe that's another generalization we can write down here. Okay, the number of loci off the page is equal to the relative degree. All right. Last example for the day. Okay. A third order model. In MATLAB, I would say G6 is a transfer function. Numerator is 1. Numerator is 1. Denominator is S cubed, 6s squared, 11s plus 6. Close it like that. Execute R locus. You may want to close all your windows and redo it, or it's going to draw in the last window that was active, so probably figured a window 2 this morning. Label axis real and imaginary. This system has poles like this. 3 poles, -1, -2, and -3. Okay. How many loci will there be? Number of loci, number of branches is equal to the number of poles. So there's 3 x's, that means you've got to have 3 loci. Okay? So we need 3 colors. Loci start at the X marks, and they go to the O's. There are no O's, so that means they go off the page. Okay? And it's going to look something like this. Let's see. -3 and -2 is -5. -1 is -6. -6. The relative degree 3 here is 3. 3 poles, no zeros. 3 minus 0 is 3. So the relative degree is 3. So I have 3 things going off the page. -3, -2, -6 divided by 3 is -2. Okay. I'm drawing in some dotted lines. 3 dotted lines that are kind of, the angle is, they're kind of symmetrically angled. I'll talk about this more on, today's Wednesday, on Friday. There's a formula that I'm calculating in my head right here. This is 60 degrees. Okay. MATLAB's not going to draw this in for you. These are just guidelines. They're guidelines. So this is 60 degrees. This is 3 times 60 is 180, and then another 60 degrees. So these are 3 lines that I draw symmetrically. Now the root locus is going to be colored in like this. There's one branch starts here and goes this way. Another branch starts here and goes this way. Another branch starts here and goes this way. So one of them goes off the page this way. These 2 come in the middle, they break. And then one goes this way and one goes this way. And as the K gets large, this control system becomes unstable. Okay? Control system's unstable when K is large. Oh, let's do one more example. We've got so many minutes left over. That'll be a 7th example. 7's a lucky number. We'll do a third process, S plus 1 times S minus 1. We'll do a third compensator. This is the, remember that picture of that boy at scout camp who was balancing the stick on his nose? Okay. Okay. I said that's similar to the idea of trying to push a rocket up in the sky. The plant is inherently unstable, so this is an unstable process. Let's enter it as a transfer function. The numerator is 1. The denominator is s squared. No s. No s means a system with no damping. And the constant term is -1. Okay, if I've done my math right, these two should be the same. Okay. C3 is a transfer function. It's a 1 and a 2 in the numerator and a 1 and a 10 in the denominator. So the picture in our mind is this. We're going to adjust the gain K. Here's our compensator, and here's our plant. It's the inverted pendulum, balancing a stick on your hand. Lead or lag? Is this a lead or a lag? It's a lead, okay? And now we're going to adjust the gain here from 0 to infinity. So we do root locus. We do a root locus plot and see what it looks like. It will look something like this. Real and imaginary. Those are the plant poles. The compensator introduces another pole way out here at -10, and it puts a 0 right here. And this thing has 1, 2, 3 poles. So there are 3 loci. So I need to draw 3 branches. I need to draw a picture that's symmetrical, top to bottom. I need to draw a picture where the branches start at the x's and end on the zeros, or they go off the page. The number of ones that are going to go off the page is I have 3 poles, 1, 0, 3 minus 1 is 2. So I have 2 of them that are going to go off the page. So let's see, I need to figure out where they're going to go off the page. And we'll talk about this more on Friday, but I'll do it mentally in my head right now. I have -10, -1 is -11, plus 1 is -10, -10 minus a -2 is -8, -8 divided by 2 is -4. So I think there's a vertical line somewhere around -4. This is just a guideline. Okay, there's a word for it that we'll learn on Friday. So the picture is going to look like this. Okay, as K increases, one of the closed loop poles will lie somewhere between -2 and -10. The other 2 closed loop poles will be somewhere in between here when the gain is small. But when the gain is large, it's going to do something like this. Okay, so this is a control system that is stable only when the gain K is large enough. Because see, this locus here is in the right half plane. So that means when the gain is low, you're going to have a pole in the right half plane. But when the gain increases, the loci move over into the left half plane. I'm not real sure, but I think if I've done this right, this this break right here, where it breaks from the real axis, is on this side of the imaginary axis. Is that correct? Okay, it's not too important right now whether I drew it this way or whether I drew it, like this, where it broke on that side. There may be some applications where you want to get that exactly right. Make sure that it breaks on the correct side. But for today, that's not an issue. We'll just kind of get a rough qualitative sketch. Okay, if I wanted to calculate what that is, there's a formula for it. But we usually will, nowadays, will ask the computer to sketch it. And then if we need to, we zoom in graphically. Okay. But the main thing to get is some of the characteristics. The loci start at the x's, here and here, and here. They go to the O's, or they go to the off page. It's symmetrical, so forth. Okay? All right, that's enough for today. Let's come back on Friday. Not here. Let's go back to our regular classroom. We're going to not draw these things using computer. We're going to draw them by hand. We're going to just review all these characteristics and do some examples by hand.